Hi everybody and welcome to the next lecture on Multimediale Werkzeuge. So this time will be about text formats and some media objects. So first let's take a look at the basics of our files on our computers. Right? So a file in a computer is organized in bytes. So each byte contains 8 bits, right? So in this way we already get some order into our many bits that we have. So one byte can be subdivided into two groups of 4-bit, and this group of 4-bit is also called a nibble. And they can be represented as binary numbers like zeros and ones, or sometimes you also see octal numbers, which basically groups 3 bits together, and this gives you a value range between 0 and 7. You also see the decimal notation. You basically take 1 byte, and 1 byte of 8 bits has a number range between 0 and 255. And if you separate the bytes with dots, this is what you use, for instance, for IP addresses. So here, maybe I can add that with dots separating the bytes. So that's the dot notation. But more often we can see a hexadecimal representation. So basically we take one nibble of 4-bit, and then we have the digits between 0 and 9. But since 4 bits can go further, we also have the letters A, B, C, D, E, F. So that gives us a range of 16 possibilities from 0 to F. And that means for 1 byte we need 2 of those digits, of those hexadecimal digits. So I should call this hexadecimal digits. Right, so when you have 1 byte, you see 2 of those. Yeah, but how do we give these bits and bytes a meaning in the sense of characters? So if we have a text, or if we have a keyboard input, we press a key, how does the keyboard communicate the letter that we pressed? For that we take a look at the history and the properties of text formats. So basically the oldest standards of computer technology. And these are also common formats, for instance, for HTML, websites, for files, and programs. So, like programs, when you program in a programming language, basically what you type in there is stored as a text format, and this is then interpreted by the computer or compiled by the computer. The oldest text standard is the so-called American Standard Code for Information Interchange, short ASCII. And that goes back a long time. So here's the history. It started in 1874 with a Bordeaux code created by Emile Bordeaux for the telegraph and the teletype. So basically the teletype, for the teletype or the telegraph, you type a key, and this key is then assigned a code of bits, and these codes of bits is then transmitted over the wire. And this was based on an earlier code of Carl Friedrich Gauss and Wilhelm Weber in 1834. You can also read more about this history in Wikipedia about the Bordeaux code. Then in 1901 it was modified. It was standardized for 5 bits, and that means we have 32 symbols. So that means it's enough for our Latin letters, but only the capital letters, plus some special characters. Numbers we could obtain with shift keys or toggle keys. Right, maybe I should say keys and toggle keys. So basically you had a special code saying now comes the numbers. In 1963 it was extended. Basically that's the ASCII code we more or less know today. So it was standardized by the American Standard Association, later ANSI, and it published the first ASCII code. It still only contained the capital letters, but in 1967 it was extended to also include lowercase letters and special characters. And this made it perhaps the most successful software standard. It is stable for over 40 years. Right, so well, now you can actually say 50 years. And it is part of Unicode as the lowest 128 characters. So Unicode is a later development which extended ASCII. And this ASCII standard has 7 bits. Right, so it's originally for input-output devices of computers, which were teletypes. Right, so basically for typing text over telephone lines, and hence also the name TTY. Teletype was abbreviated TTY, and in Unix or Linux you can still find the name TTY for input-output devices. So you even have the command TTY in Linux, which gives the name of the input device connected to the standard input. And the input devices and many TTYs are listed under /dev in Linux. So we can actually try it here with my terminal. So I can say TTY, and it says dev PTS 0. So that's the name here basically of my standard input. So when I then list ls for list, see what's in the directory dev, then we can see in this directory dev for device, we see many TTYs for teletype. So these are basically special input outputs that we have to our control. And you can also see std in and std out. This is standard input and standard output. So basically the terminal here I have opened. When I write something to std in, it appears on the terminal. Or if I type something on the input, you can read it in standard input. And if I write something to standard output, it appears on the terminal. So in this way we can actually get messages from the terminal, which I type, or to the terminal. So we can use that actually in programs to control input-output. Then there's also this std_err. So this is where error messages are sent to by default. There's also SND for sound. So this is actually an easy interface to access the sound card. Again, reading, writing, so you can access microphones or write to the speaker, which is also quite interesting. Yeah, so this makes it quite universal. So here we can now see the ASCII code table. So on the left-hand side, you see the numbers 30 to 120, and on the top from 0 to 9. So for instance, the exclamation mark, it corresponds to the ASCII code 33. Then you have the number sign 35, $sign 36, and so on. And here you can see the A corresponds to 65, the Z corresponds to 90, And here now come the lowercase letters. So 97 is lowercase a, 98 would be lowercase b. Right, and you also have curly brackets, square brackets, backslash. So basically here you have all the signs you would need for programming, and this is actually also how programming was originally done, exclusively with this ASCII code table. So in programming languages you find no letters which are not appearing here. So here you can see more about it here in self-html.org. And here you can also see that there are no umlauts, right? No Ö, those German special characters, they don't appear here, because originally it was just for the English language. Yeah, so later there was an extension for further languages, including the umlauts, using the 8th bit. So here is the extension for Western European languages, German, French, and here you can see that the umlauts are indeed here, right? And also other special characters from other West European languages. So basically this starts with 160, right? So here we are basically extending this code range to above 128. So here, for instance, let's see, the A is 196 and the lowercase a is 228, right? So again, this is from self-html.org. Yeah, you could also ask, what about the first 32 ASCII characters? Going back to this table here, you notice it starts with 30, or basically the first characters here is 33. So what about the lower one? So the first 32 ASCII characters are actually control characters. You can actually find them in ASCIIcode.com. And they are unprintable control codes and are used to control peripherals such as printers. So here you can see them. So here you can see the code as decimal, octal, hexadecimal, and binary. And this is then the symbol they represent. Right, so here you have the symbols. And you can see it's all special functions like bell, like sounding a bell. This was useful, for instance, for teletypes. When a message was completely transmitted, then it could sound a bell to tell the operator, now we are done with our transmission. Or something that is more useful nowadays, form feed and carriage return. This is actually indeed used for text, ASCII text, to mark the end of a line and the start of a new line. Right. So when you type the return, then this is usually symbolized by either form feed or carriage return. It's slightly different. There are slight differences between different operating systems. For instance, Windows uses both, and Linux uses, I think, just carriage return. So there's more. End of medium, escape. So this is also still widely used when you press the escape key. This is the code for it, the 27. Yeah. So here you see decimal 27, octal 33, hexadecimal 1B. And here is the binary code. Yeah, so these are basically the control codes which appear in the first 32 ASCII numbers. File separator, this is not really used much anymore. Yeah, and in 1985 there was an extension to 8-bit code by ECMA, the European Computer Manufacturing Association, standardized as ISO 8859. So this is actually what we just saw, for instance, for the Western European languages, is part of this standard. So the resulting upper 128 characters contain the special characters in different languages depending on the version. So there's not just Western European, this has the number 1, but there's another one, number 2, for Central European, number 3 is for Southern European, number 4 is for Baltic, Cyrillic, Arabic, Greek, Hebrew, Turkish, Nordic, Thai, and so on. So you can see there's actually many different versions necessary because the 128 upper numbers are not sufficient to display all those different languages. So there needs to be one version for each region. And this is actually complicating things because we have ambiguity. If you write a text file with special characters from one region and you want to display it in another region, then you have to tell the computer to use that according extension. Yeah, so this is also from Wikipedia, ISO 8859. So because of this ambiguity, Unicode was defined. And this ambiguity also shows up when you use your editor, for instance, and read a file from a different region and it uses special characters, then it doesn't necessarily display those characters correctly. You have to then tell the editor which extension to use. And this is simplified by Unicode. Unicode basically standardizes those extensions in a way that you don't need to know what code alphabet was used originally. Yeah, it was standardized by the Unicode Consortium and in 1997 by the International Standards Organization, ISO. So in 1998 it made version 2.1, then in 2000 3.0 and in 2001 3.1. And it usually uses 16-bit instead of just 8-bit. So in 16-bit you can display approximately 65,000 characters, and that's sufficient for all those different regions we just saw. But there is also a version with 32-bit, which gives you approximately 4 times 10 to the 9th characters. And that's important, for instance, for Asian languages, which have many characters. Basically, there one character represents one word, and then you have tens of thousands of different characters. Yeah, but that's a little bit long for general use, so that's why usually shorter versions are used. Yeah, and various character sets are available in so-called scripts. So in a nutshell, it began with the Latin alphabet, then Greek, Cyrillic, Hebrew, Japanese, Hiragana, and Katakana. Chinese characters, they have approximately 21,000 characters. And we have approximately 6,000 codes for company symbols. So often used is the 16-bit version, which is called UCS2, Universal Character Set, or UTF-16. This is actually the more common name, UTF-16. So often nowadays we have UTF-16 when we have an editor. There's also a 32-bit version which I mentioned, which is called UTF-32 or UCS4. And there's also a UTF-8. So that's an abbreviation for 8-bit Unicode transformation format, and is the most widely used encoding for Unicode characters. So note that here we have the same number of bits as we have for ASCII codes. But we saw ASCII codes have this problem with special symbols. So how do we solve it there? So in UTF-8 we actually have unequal character length. So for instance, German umlauts are presented by 2 bytes, unlike ASCII, where it's still only 1 byte. And this is how the ambiguity is solved for the special characters for different regions. If we have special characters that don't fit into 8 bits, they get 2 bytes. Right, so that's the specialty, that we have different length. Yeah, so we have the advantage of having only 8 bits most of the time, but still have unique special characters, and they are using 2 bytes or more. So in the lowest range, in the first 128 characters of UTF-8, this corresponds exactly to the ASCII code, so it's backward compatible. The highest bit is 0, and the remaining 7-bit combination is the ASCII character. So you can also read more in this Wikipedia page about UTF-8. So in conclusion, text formats give us long-term stability, very important for documents or computer programs. They give us interchangeability across all possible computer platforms. Again, important for documents and computer programs. And they give us flexibility for the presentation of multimedia content through languages such as HTML, SGML, or LaTeX. So these are documents or websites. Yeah, so here are some examples where we can actually see the differences between them. We can view different text formats using the Linux or Unix command od for octal dump. So this is actually the command. We can give it a different font. So here od in the terminal lists the content, the binary content of a file. So with an editor, for instance gedit, we can create a text file. For instance, with the words, this is a test, and then some special characters, some special German characters, and save it in different formats. ASCII Western European, UTF-8, UTF-16, and UTF-32. And in gedit, it's easily possible with file, save as, character encoding, add or remove, and then the appropriate selection. And then we save, for instance, in the first case with the name test western ASCII.txt, so that we remember which it was. And then we can actually look at it using od and see what's inside. Yeah, so how do the resulting file sizes of those 4 files differ? So for that we can again go to our terminal. So the terminal shell, and now we say ls minus l for long, and then star.txt. So now it lists in long format all the files. Star means any characters in front of the dot, and with the ending txt. So this is what we have here. And minus l means it also lists the length or the size of the file. So let's take a look. So here the test files are the ones that are already generated using gedit. And now we can see here test western ASCII.txt. And we can see it's 24 bytes. So it's actually nice and short. Then we have test UTF-8.txt, and we can see it's 28 bytes. So we can see it's slightly larger than the ASCII version, and that's because those special characters are represented by at least 2 bytes. Right, so we need a few more bytes. Then we have the UTF-16 version. It has 50 bytes. So it's actually slightly larger than twice as much as test western ASCII. And that was to be expected because instead of 8-bit, it uses 16-bit per character. And then it has an additional byte in the beginning. And then UTF-32 has twice as much as UTF-16, again to be expected because it uses 32 bits per character. So using the command more, we can display the content of this text file as ASCII characters. So first I can start with test Western ASCII. So more than just displays the content as ASCII characters, which fits in this case. So here we see this is dein Test. So actually the content is slightly different. Should be dies ist ein Test. And you can see more does not recognize special characters. It just displays them as little question marks here. Right, so the command more in Linux is made for the original ASCII without the extensions. So now we can try UTF-8, copy, so more UTF-8. And interestingly, here now more knows how to display the umlauts. And this is probably because UTF-8 now has no ambiguity anymore what those special characters are, because there are no different extensions, but each special character is defined uniquely. And hence we can make a command more such that it uniquely displays those special characters without having to know which extension we used. So the ambiguity is gone, and hence that's why we can now display those special characters correctly. So now let's try UTF-16, copy, so again more, display the content, and again, well, not again, now it has problems. It doesn't know how to display UTF-16. So more is fine with UTF-8, but it doesn't really know how to display UTF-16. And let's see if it knows how to display UTF-32. As expected, if it doesn't know UTF-16, it also doesn't know UTF-32. So you can see UTF-8 is actually a good choice for universal compatibility, because here even my more from Linux knows how to display the special characters correctly. Right, so we saw the different sizes, and we saw that more is compatible with UTF-8. And now we can actually take a look at the binary representation using our OD command, octal dump. So here we can take this command, and -C means that it also prints the ASCII characters. Right, so let's try test Western ASCII. So here the content of the file is displayed byte-wise, where each byte is displayed as an ASCII character or a special character. Right, so yeah, so this is now similar to more, but it has a more detailed display. It also displays the byte number here. So here we see dies ist ein Test. And here we can see now the special characters as numbers, right? And here we can see \n, which stands for return. Right. And now we can also compare it with UTF-8. Let's see what that does. Again, as character. So it looks quite similar. Dies ist ein Test. But then here for the special characters, it differs. We can see we get more numbers. Right? So here we have one of those numbers for each special character. Now we have more of those numbers, which means we have more bytes. Right? We have 2468. So which means we have 2 bytes per special character. So as expected, UTF-8 uses 2 bytes for our German special characters. Then we try it for UTF-16. So paste. And this looks interesting now, because in UTF-16 we have 2 bytes here in the beginning, which are extra. And basically those 2 bytes tell us something about the format here. And then we have our letters. The D is still there, but then there's the next byte, which is all 0. Right? So this is basically the remaining 8 bits. So in UTF-16, if we have a letter which also appears in UTF-8 or in ASCII, then the encoding for the first byte is as it was before, but then it's filled up with zeros basically. And this is what we get at each of those letters. Right? We have those filling bits and they are all zeros. So we basically have 8 zeros as filling after each letter. And then we see again our special characters. Now the special characters don't have a special length. They're again also 2 bytes. And here you can see it's actually the same numbers as we had for Western ASCII, but with those fill bits here. And then we can compare it with UTF-32. So UTF-32. So here you can see the same structure. So you have those beginning bytes here again, just like UTF-16. And then you also have 2 bytes which are 0, which we didn't have in UTF-16. And then after each letter we have 3 fill bytes, right? So basically most of those bytes will be 0 now to fill it up to 32 bits for each character. Similar here for the special characters. You have the special character numbers and filled up by 3 bytes of zeros. So you can also see here that it's kind of wasteful, mostly zeros, and that's also why usually you don't use UTF-32. Most used is UTF-8. Yeah, we can also use CU1 as an option for OD, and there you can also see the decimal representation of the bytes below the ASCII characters. So I can try that maybe with UTF-8. So we can say -T CU1. And here we can see the letters, space, and here is the ASCII characters as decimal numbers. So here you can see D, capital D, is the ASCII number, ASCII code 68, lowercase I is 105, space is 32, so this is actually the last of the special characters, the space, the control characters, 32, and then here you can see going on with letters, and here we have the special characters, and here you can see below the corresponding ASCII code. So here are basically the extension of the ASCII code. And you can also see that they are now 2 bytes. So when we now compare it to my ASCII code example, so test Western, special letters here, special characters 366 and ASCII code 246. And can we see it here? No, here there's a different code. So here it's not really corresponding, basically also like we expect, because we have different extensions, and for different extensions we have different meanings for the same code. So we need to distribute out those different characters over different codes. Yeah, let's try 16. So here we can see if you use UTF-16, we still have the same code for the lower byte, and then it's filled up with zeros. So same as before, and here come the special characters then. Yeah, so you can see basically UTF-8 is the most practical, although you need to keep in mind that it has a variable character length, a variable code length. Yeah, so what happens if instead of an editor we use a word processor like LibreOffice, which produces the .odt format, like for instance I do here with my slides, right? We can open a document, write the same words, and then save the document as test.odt. So now we can take a look at how big it is. So let's do the same thing, ls minus long, and then test star.star. So now we have all the test files. So here we see the text files before. We can see we have a maximum of 100 bytes. But now we have the ODT version. This has 9134 bytes. So this is almost 100 times as big as UTF-32. So if you didn't like UTF-32 because it was wasteful, the ODT format is actually 100 times as wasteful. Right. You can also save it as XML. Then basically you get exactly the same size. And this also shows you, gives you a hint what's happening. So XML is a extended markup language where you have also formatting information and additional information in it. And this is basically what you have when you use a word processor like LibreOffice. There you not only have the text itself, but you also have information about what font to use, what size, where to place it, who's the author, and so on. Lots of information. So we can actually take a look at it, again using OD-C, displaying the characters. And let's see what's in it. So here you can see it. You can see lots of information, too much. So here's the beginning. Let me scroll to the beginning, and you can see here there's information, then MIME type application vnd.oasis.opendocument.text and so on. So it has plenty of additional information. Let's see how it looks like when I say more. Yeah, it doesn't really work for more because there are too many special characters which it cannot display. So here we really need OD. And if we have too many pages, we can actually pipe it to more because the output is now displayable by more because it only contains displayable characters. But then we have the advantage that it displays one page at a time. So again, here's the first page. Here again we see MIME type application vnd.oasis.opendocument text. Let's see XML. Here you can see meta.xml. So we see it's an XML format, and that's why it also basically we get the same thing when we export it as XML. Here we can see the version 1.0. Encoding equals UTF-8. So here we can now actually see that this XML code, this .otf ODT format is actually encoded using UTF-8. So this is another application now for UTF-8. So internally it uses UTF-8 to display all the store all the information. Here you can see more. Office, document, redundant information basically. Let's see if there's more interesting stuff. Meta, date. Here you can see date 2013-04-22. So this is the creation date. T 15, 20, 30. This is probably the time. So it contains lots of information, meta information about this file. And you can imagine when you write a program, you don't need it. And you could give it a compiler or a browser, because then it wouldn't understand it. Right. So yeah, we can see that there are a lot of formatting commands of the word processor in the file. If, for example, we want to write HTML files, we want to use our own HTML commands. Therefore, it is important to really save this file in a text format, like UTF-8, which a browser can recognize and interpret. Right? So if you want to write HTML documents, you have to do it using an editor, or export your document as HTML format. So for instance, here my LibreOffice can also export as or save as, let's see, save as, yeah, there's XML, for instance, and here there's also an HTML. So you can also save it as HTML, and then you have an HTML formatting. But without all the possible capabilities. It's just the text itself. Yeah, so here's an example for an HTML code. An HTML page starts with this HTML tag. So arrow left, arrow right, and then comes the page itself, and then it is ended with /HTML. So now again we can do the same game and save it in different text formats, UTF-8, 16 and 32, and then open it with different browsers and see what they do. Right, so let's see. So we have ls_star.html. So here we have HTML test. Let's start with Western, copy, and now Firefox, and then give it as an argument. The file should display, and now it should start Firefox displaying just this page, hopefully. Yes, now it starts. Oh, interesting. These design test, and this is how the umlauts look like. It seems my browser thinks that it's some Asian font that it should display. So it recognizes that it is probably Western ASCII, but then it has the wrong extension. So the expected ambiguity. So that didn't really work so well. So that's why we usually have UTF-8. Right, let's try the same for UTF-8. Firefox, UTF-8. So when I end here with this ampersand sign, that means I can still use my terminal after starting this program. So then the program starts in the background, which I'm actually using now. So the program is still there, still active, but I can still use my terminal because I started with this ampersand sign in the end. So yes, so now you can see a good reason for using UTF-8 is because browsers understand umlauts. And that's when you use, or previously, HTML had special commands for special characters, like umlauts. But if you use UTF-8, you don't need those special HTML commands for special characters anymore. So an important advantage for HTML8. So let's try the same for Chrome. Chrome, HTML, let's try Western. Test Western, again with an ampersand. I think it should be Chrome browser. No, it's not working. Oh yeah. was an where was my Chrome? Here's my Chrome. Well, let's try Chromium. Chromium, yes. Let's take that one. So interestingly, Chromium now displays the special characters correctly, probably because it assumes that it is a Western extension that I'm using correctly. So now let's try the UTF-8 version. UTF-8. No. UTF-8. And again, as expected, it displays it correctly. So now we can try UTF-16. Let's see what it does with UTF-16. Again, the right thing. So now try Firefox with UTF-16. Yeah, so Firefox again displays it correctly with UTF-16. So now try UTF-32 with Firefox. Yeah, and it's not quite correctly because it displayed the HTML tags also as part of the text here. So UTF-32 is only half working. So now let's try the Chromium browser. UTF-32, similar. So here it also displays the HTML tags as text. So UTF-32 is not quite working so well for browsers. So again, UTF-8 is a good choice, right? It seems UTF-8 is a standard which everything and everybody understands. Yeah, and also even for Android, for the Android operating system, you can get a terminal application. For instance, you can get a terminal IDE and BusyBox from the Play Store for free, and then you can actually use commands that I just as I just did on Android, because basically Android is also a Linux type operating system. So in the core, Android has Linux, and that means if you get such a terminal IDE or the terminal application, then you can use those commands. Yeah, so another advantage of Linux is really widespread. Basically any Android smartphone is based on Linux. Yeah, then more details about HTML. So here we have text objects and properties that we can define, like the font type, the font size. So here maybe I can write type, the size, the positioning, and hyperlinks. And HTML editors can easily create HTML pages with formatted text, including hyperlinks and also images or drawings, by exporting as HTML. And even LibreOffice can export text, formatted text, as HTML. But then the HTML source file becomes large and is no longer well readable by humans. Right? It's understandable by browsers, but not really by humans, because it's too cluttered. Also, HTML has more possibilities. It is more like a programming language. For instance, it can have external definitions via style files. And also, very important, small programs in Java or JavaScript cannot be made in a word processor, but HTML can use them. So further capabilities are multimedia objects that can be included, like sound, video, three-dimensional models that can be viewed and rotated in one window, or similar sound, image, video objects. So there are different formats, for instance, uncompressed, compressed, different compression modes, different playback modes. So quite a lot of multimedia capabilities. And that's particularly true for HTML5, to which I come later. But first, JavaScript. So JavaScript is basically a programming language which can be executed by our browser. So applications and properties are for automation, for instance, image changes when you move the mouse over it, or inputs that are processed further, for instance, for calculations, like a small calculator in a website. We can open, close, and resize new windows. It is a script language which is executed on the local computer, the client. And it is not a binary executable like you would get when you compile a program like in C. The script is interpreted on the local computer, which means it is slower than a binary executable and similar to BASIC in earlier computers. It is also platform independent, which means it runs in the browser, which means everywhere where the browser runs, the script runs. So that's also a big advantage. Yeah, so here's the history for it. It started in the 90s. So in 1995, there was an object-oriented scripting language originally developed by Netscape and Sun. And in 1996, Microsoft and the Internet Explorer 3 was JavaScript capable, but calls itself JScript for legal reasons. And it has its own extensions, or takes its, but has its own extensions and variations, which makes it only partially compatible. So it's only essentially compatible, but not all the way. So that is kind of annoying for website designers, because they have to check which browser is used on the other end. In the meantime, those differences became less. So it seems Microsoft wants to be less different nowadays. Yeah, in 1997, the Internet Explorer 4 with language capabilities of JavaScript 1.1 came out, but also own incompatible language extensions. Then in 1998, ECMAScript was standardized by ISO. So here international standardization came into play, and Netscape made JavaScript 1.4, which is compatible with ECMA 262. 2002, the Mozilla organization, Mozilla 1.0 came out with JavaScript 1.5. And JavaScript has similarity to Java. The syntax and some keywords are comparable, but we have a different system. Java is a programming language to compile. JavaScript is an interpreted programming language for the web browser. And for it to work in a web browser, we need a document object model, DOM. This is basically representing memory for inputs in web pages, for instance, forms. It gives us a memory structure, and it gives us a data and object interface for JavaScript. Right, so this is basically what connects JavaScript and HTML. And this was standardized by the World Wide Web Consortium also in the 1990s. And yeah, this provides functionality, for instance, for input-output for JavaScript. and you can read more in this Wikipedia page on unicode.eworkers.de. Yeah, now we also have some JavaScript examples, which are also on Moodle 2 and our website. For instance, this drag-drop.html. Let's see if I have it here. Star.html. Drag-drop is not there. Yeah, here, JavaScript. So here we have it. Drag-drop. So here you can see this drag-drop, and we can copy and open it, for instance, with Firefox. So here you can now see the web page with text. So here you can see the text and with two images. Right. So here are two images from a webcam in Berlin some time ago in the 2000s. And now you can actually use the mouse and the left button for shifting them. So here, click, left click, and I can drag it. So drag and drop. So when I lift the key, then it stays there. So that's actually quite a nice demo. And we can actually resize the images with a shift button and the mouse simultaneously. Let's see. So oops, that's not what I wanted. So shift, I'm now clicking shift, and now left mouse button and dragging. So now I can actually change even the aspect ratio. So now I can see what it is. So here you can see the old Palace of the Republic, which is no longer existent. And we can do the same here. Shift button on the keyboard, and now open it. And here you can see a parade here, or a demonstration. So that works nicely. And this is mainly done using JavaScript. So when we look at it, we can say more, drag, drop. So then we can see here's the header. This is what is displayed in the new in the window. And here you can see JavaScript starting. So here you can see first the background color here. So here body BG color equals, and then this is a hexadecimal representation of the three primary colors. So 53 is hexadecimal for the intensity of red, A7 is the intensity of green, and 8C is the intensity of blue. So this basically, this gives us a color mixture, which is then the background color. Here's the text that appears on the page. And here we can see the script is imported from a separate file. So here you can see first it tells the browser what type of script it is, JavaScript. Remember, we had different variations. Then here the source file. So this is the name of the file in the same directory, and that's why I'm not specifying any absolute directory here, no absolute path, but just the file name because it's in the same directory. And that's it for the script. Right, so basically it imports all the functionalities from this separate file. Yeah, so then here it then imports the file, this first picture. So here you can see image. So here you have P for paragraph, then you have an image which is displayed on the right side of my page. Gives it a name, and then here it reads this image again from the local directory and gives it the width and the height. And also an alt now makes a connection to this JavaScript. Alt means this is what's displayed when the image is not found. So here gives it a short description. So here the same for the second image, and then yeah, that's basically the end of it. So here script is ended, body is ended, HTML is ended. So then we can take a look at this JavaScript. And this is a little bit more extensive, and that's why I'm opening it with my editor, gedit. So now we can take a look into it. And here we can see it actually has 1,400 lines. So this is really a big program, right? And here you can see it looks a little bit like Java, or it also has similarity to C or C++. Here you can see a for loop, object-oriented, this dot. So this is a object-oriented language. Yeah. So I'm not going into the detail because this is a little bit too complicated, but I have another example which I'm going to show you. First, another cool graphical example here, slide rule. So here we have slide rule. Slide rule. So here we have the HTML page. Copy, open it with Firefox. And here you can find a slide rule. So this is kind of something like out of a museum. This is what people used before they had pocket calculators or computers. You could use the slide rule to multiply two numbers. So you did that by searching the first number, say 2, on the lower part of the slide rule. So here's the 2. And then you want to multiply it maybe with 3. So then you have this middle thing, this middle tongue here, which you can move. And now JavaScript makes it movable, again using mouse and left button, but only horizontally. It doesn't let me go up and down. So this is an example for restricted movement. So same here for this hair. And now you can move the 1 on top of it. So this is what you do when you do multiplications. You move the 1 on top of the first number. Then you can also move the entire pocket slide rule. And then you, maybe if you want to say 2 times 3, then you have to look up the 3 on the middle part here. Here's the 3. And then if you go down, you have the 6. Right? So this is how you can multiply two numbers. So basically this is done by adding logarithms. So if you have if you add two logarithms, then it's the logarithm of the product of the two. And so the length that you see on the slide rule here is basically the logarithm of the number. And that's also why the distance here becomes smaller when you go to higher numbers. That's because the length of the higher numbers grows slower when you go to higher numbers. Same here in the middle part. You can also flip. You have a button here which is doing flipping, and now you can use the flip side for unit conversion. It's also kind of interesting. So for instance, you can convert let's see, kilometers and miles, meters, feet. Where do we have miles? Here you have miles, and where do you have kilometers? Meters, square kilometers. You have meters. Meters to feet. Oh yeah, here, kilometers, right. So say you have 10 kilometers, right? Here you have the 10 above, then you set the mark for kilometers on it. and then you look up the marking for miles, and then you can see it's 6.2 miles roughly. Right, so it's quite convenient, and this also gives you a kind of a visual interpretation. You can see that miles is less than kilometers, so it's kind of nice, and it works without batteries, and it's easy to fix, so it's actually quite practical. The only disadvantage here is that you have to know the order of magnitude. You note that this goes from 1 to 9. So if you have, say, 1000, it's still a 1, right? Then basically you have to memorize the exponent of 10. This is just for the digits, but not for the comma. Basically you have to know where the comma goes. Okay. So there's another example which I made myself, the GS SciCalc, which I want to show you. So this is basically a scientific calculator which you can use. So let me open it with an editor, gedit. So here you have a scientific calculator as a web page. And this has the advantage that you can also program unusual functions, mathematical functions, which you usually won't find on a pocket calculator. In this case, for instance, a check for a number if it's prime or not. And it uses some very fast statistical algorithm to check for primeness of a number. So this also works for really large numbers, which is actually used for designing public key cryptography. So you could use this scientific calculator for designing public key cryptography. So here you can again see how JavaScript is working. Just in this case, the JavaScript part is inside the HTML page. So again, here you have the title, which appears in the title part, title bar of your web page. And now starts the script part. So here again, type JavaScript. And here now you can see the JavaScript code. So here you have function, a function definition. This is how a function definition looks like. Init Rechner, so here it does some reset, defines variables here. And here's a function. This is basically a big function which I'm using. It uses 3 numbers as input and an integer n which tells the function what to do. And here you can see the switch command, which basically switches according to the number which is in n. Right? So depending on what's in n, it executes different operations. And this is basically what then the buttons on the calculator will do. For instance, here it generates a random number, or here it computes the greatest common divisor between 2 numbers, and so on. So it has lots of functions here. Right, here you have a function enter, which is basically when you, for the enter button in the calculator, here's the function prime test, and prime test itself calls more of those functions. For instance, here this expon is another function, GCD is the greatest common divisor. So this is actually the statistical method, probabilistic method for testing for primeness. Then here's another function for this test. Here's this exponent function for integer numbers. Here's the greatest common divisor as a function. And yeah, that's it for the Java part. So JavaScript part. So here's the end of the script. And here begins now the head, where I define the background color of my web page. So again here, the 3 primary colors, red, green, and blue. And here you have 2 hexadecimal digits for 1 byte again. And here you have a form, which basically means we have input, output, and buttons. So this is what now connects my JavaScript to the HTML part. So here we have a form, we give it a name, Rechner. We have an action which is not really present here. And on submit, this is what it's doing when I press the enter key on my keyboard. And here it defines input fields. So we have 3 input fields, Z, Y, and X is also the output. So here we define it as input, give it a type, text. So basically it takes keyboard input, then we give it a symbolic name, Z-Wert, Y-Wert, X-Wert. This is what I will use to access the content using our document object model. And here I give it the size, meaning 80 characters wide. So it's quite a lot. So BR means new row. Then here I have a new input. And this time the input is a button. And this button gets the name and the value reset. And this is the action that it should take when I hit this button. It calls the function initRechner. Then I have another button with the value undo. So this is the text on the button. And this is what it should do when I click it. Right? Here you can see it does 3 assignments. So here document Rechner x-Wert value equals x0. So this is an old stored value from this x-Wert, and it's going back into this input field. So when you look at the syntax here, document is the current document, the current HTML document. Then Rechner is the name of the form that I defined here. See, here's Rechner again. Then .xWert is this input field here, this last input field. So it has this name, and now we can access it using this name. And value means it now accesses the value which is inside, right? The number that I type in is the value. And here, since it's on the left-hand side, basically the value is assigned this x0. Right, so basically in x or x old, y old, z old. So basically we recover the old values using the undo button, which also is something that most pocket calculators don't have, but which is sometimes very practical. Basically, if you input something wrong and you want to go back, then you type undo. Yeah, so then you have more buttons. So here you see more functions. For instance, here the addition. So here I add 2 values and the result is then displayed in the X field and so on. So here all the buttons are defined, and since I don't define where they should be, they are basically appear in the same order in which I define them here. And if they don't fit in one row, then a new row is started. So that's also good for flexibility. For instance, if I resize my window, or if I have, for instance, a small screen on my smartphone, then it's adapted. Here we get all those buttons. And this is then the end, new row, and here's the end of the form. So this is the end of the form containing the input fields and the buttons. And then I'm adding some formatted text as an explanation how to use it. So this is the text that appears on this website. So then here's the end of the body, and here's the end of the HTML page. So now let's see, execute it. And you can see this is actually from 2008, and it still works. So very long time stable. Firefox. So let's see if it opens. It's kind of slow. here you go. So maybe I can close the other windows. So here you can see now my scientific calculator. Here you can see the header text on the top. Here you can see the 3 input fields. Here you can see the buttons with the different functionality, and below the text as a description. And you can also see when I make this window more narrow, then it adapts. So the fields adapt, and also the buttons are be distributed. So that's kind of nice, because basically the browser takes on the role of doing the fine formatting. So here I can do, for instance, my addition 2, 3, and then I say x plus y, and the result appears here in the x field. I can also click undo, and then the old numbers reappear. One interesting functionality is also the store recall, which uses cookies. Cookies are memories for our website, which we can access using JavaScript. For instance, 1, 2, 3, 4, we can say store, then we can say reset, everything is deleted, but then I can say recall, and then our number comes back. And that works because we have cookies. And we can see this function here also in my code here, HTML code. Here the last 2 lines define my cookie buttons. The first is the store X, and this is how it works. On click, and so when I click this button, this is executed. Document.cookie gets equal document.rechner.xwert.value. So the value in X is then stored in document.cookie. So this is a variable which allows us to access the cookie for the website. When I say recall X, then I take document.cookie and reassign it to the X value field. Right, so easy enough. Just this variable document.cookie allows us to store and recall information. So this is actually what you see almost every time when you open a web page. The announcement, we are using cookies. That means that there's some information is stored for this web page on our computer. But this is basically the only way we have to access memory on our computer. There's no other way. We cannot access other files on our computer. We only can access cookies, which are assigned to this web page. So usually they are used to store some setting when we visit the web page, so that we have the same settings next time, or also for advertising. So if we show some interest into a product, then maybe next time we visit this web page, it reminds us that we had interest in this product. Right. Okay. Yeah, so this shows you the basics of JavaScript. So finally, there's the portable document format, which is also based on text. And this is around since 1993, was introduced by Adobe. And this is a platform-independent print representation, unlike HTML, which leaves the fine formatting to the browser, as we just saw. And this format is used as a description language for documents and is related to PostScript, short PS. But PostScript was intended only for printers. But unlike this, it is no programming language. So PostScript was quite versatile. It even had kind of a programming language. But PDF has more possibilities for document description. It also has a password protection. possible for printing, for copying in the clipboard, or for document change. And although a description language, minor changes, for instance to correct typos, can be made in the PDF file if it's stored as text, right? We can actually open it with an editor and try to make changes. Also in operating systems, for instance in Apple, it is to make sure that the screen input, the screen image corresponds exactly to the print output. We can create PDF documents using, for instance, Acrobat Distiller, or we can create a PDF file when printing to PDF. And that's basically in all operating systems. Interesting is also the possibility to add comments and markers to PDF files, for instance, for corrections or feedback to the author. It supports vector and pixel graphics. So often when you have graphics, that's not in text format, but really binary. So it's not completely text-based. Vector graphics are, for instance, fonts or predefined objects. They can be scaled, enlarged without losing quality. PDF supports arbitrary fonts, can be loaded into PDF files and then displayed. Pixel graphics can be used to display images, photos, and scans. For instance, when scanning documents, embedding images in documents. Links are also possible, similar to HTML. For instance, when you have conference proceedings as a collection of articles and papers of the conference, then you have links from the name of the author to the paper, or links from the table of contents to the corresponding chapters or papers. Yeah, so that should be it for today. Thank you for your attention, and then see you next time.